We are ready to begin the first of 4 possible ways of determining the delta H of a reaction, and this way involves calorimetry. There are 2 major types of calorimetry. There's bomb calorimetry and coffee cup calorimetry. Great names. If you were to get a little more scientific with the names, a bomb calorimeter is a constant volume calorimeter, and a coffee cup calorimeter is a constant pressure calorimeter. So we're going to look at the components of those calorimeters, and we're going to learn how to work through calculations for them. All right, so constant volume calorimeter is, first of all, let's define calorimetry. What do I mean by that? Calorimetry is the process of doing actual measurements to determine the delta H of a reaction, or the heat given off by a reaction. So we're going to be making measurements of temperature change to the surroundings to know what's happening inside with the reaction. It is the most challenging of our ways of determining the delta H of a reaction because the manipulations we have to do mathematically really require a good understanding of thermochemical equations and how to utilize them. So we'll spend a lot of time really analyzing how to work through these problems. Now, the other methods that we'll talk about have as their basis the calorimetry, but they've come up with ways to take the measured information and do manipulations with them, and we'll find that the other 2 ways are not as challenging for students as the calorimetry are. Okay, so we're going to determine the delta H of a reaction typically with calorimetry by measuring what's happening to the surroundings. So a reaction is taking place. This reaction is either giving off heat to the surroundings or is absorbing heat from the surroundings, and we can't know the amount of energy given off by the reaction or absorbed by the reaction directly, but we can easily measure what's happening to the surroundings. So we just stick a thermometer in the surroundings, we know how much quantity is in that surroundings, and we use our heat information, those heat calculations that we learned about in a previous section. Okay, so we know that whatever is happening to the surroundings can be related to the reaction. It's the exact same value, but opposite in sign, and I think I'll have that mathematically, no, I don't have it mathematically written down there. Let's mathematically write it here. So the Q of the reaction is equal to the negative Q of the surroundings. So there's the same magnitude but opposite in sign. We can't know this directly, but we can easily measure this. We can know how much heat the surrounding is absorbed or losing, and we know that they have to be equal but opposite in sign. So that is a foundational piece of information, so we got a red box around it. It is a foundational way of writing it equation-wise when we're dealing with calorimetry. So what we see here is a schematic of a bomb calorimeter. And let's talk about what's going on in a bomb calorimeter. First of all, we use bomb calorimeters to measure the enthalpy change, delta H, when a combustion reaction takes place. And typically, the combustion reaction involves, or it can typically involve, carbon, hydrogen, and oxygen containing compounds. When that occurs, we know that complete combustion will form carbon dioxide and water as the products. So if it's a solid or a liquid, what we can do is we can put that compound inside this little cup here and measure out exactly how much goes in, and then we surround that with a high pressure oxygen. So it's got a valve there where you can pump it full of a lot of oxygen. And this will ensure that complete combustion takes place and we get the carbon dioxide and not carbon monoxide or not soot. It goes completely to those 2 products. We have a little wire running down in there that we can spark it to get it to ignite, and there's going to be this little explosion in there where it just suddenly, boom, has the combustion reaction take place. That's contained in a strong metal container that can't itself blow up, okay? So it's a thick-walled container that can handle high pressure and the little explosion that takes place inside. But as soon as that happens, we're going to also get heat released. Combustion reactions always give off heat. So the heat's going to be given off and it's going to be absorbed by the components of the calorimeter, but it's also going to be absorbed largely by the water. We measure out exactly how much water it's sitting in We stick a thermometer in there and watch the temperature rise on the thermometer. And we can take that little equation that I had written on the board, that Q of the reaction is equal to the negative Q of the surroundings. And we can, from knowing what the surroundings are doing, know what the reaction is doing. All right, so what we do is we're measuring a delta T for the reaction. We can calculate the heat of the absorbed by the surroundings, and from that we can determine the delta H of the reaction. How are we going to do that? Well, this is not a constant pressure environment. The pressure is changing, and Q is equal to delta H when it's constant pressure. So we're not directly going to be able to relate it, but it's not a hard step for us. What we actually obtain from this is delta E of the reaction, okay? But since there is no work, the delta E is equal to the delta H. Remember, delta E equals Q plus W. And since we can't change the volume inside of there, the work term is 0, so we are getting the delta H of the reaction when we do the bomb calorimetry. So that is the components of that calorimeter. The other calorimeter is the constant pressure calorimeter. In the constant pressure calorimeter, we sometimes call it a coffee cup calorimeter because it can easily be insulated with styrofoam. Okay, so we would often do this for things where we're aqueous reaction. It's taking place in aqueous solution. In other words, it's taking place in water. And you can just let the reaction take place directly in that water. You can, again, stick a thermometer in there and measure temperature changes. When you measure those temperature changes, you're calculating the Q of the surroundings, okay? So the solution is the surroundings. And we'll assume that the coffee cup insulator is keeping it from going anywhere past that. And once we know the heat absorbed by the surroundings, we'll know the heat of the reaction. And since it's taking place at constant pressure, that would give to us a delta H of a reaction. So that is the background of calorimetry. We are measuring temperature change. We're going to keep in mind that the Q, when you're measuring heat change of a substance, by measuring its temperature change, we have this equation. So we will utilize that equation as we work through the problem. So let's work a couple of them. Okay, now let's look through what it says here in this problem, and I'm going to have you stop and think about this question before we actually do the calculation together. So what we're doing is we're taking some calcium chloride and dissolving it in water. When it dissolves in water, this is the reaction that takes place. It just breaks apart into its ions. Now we see that the temperature rises in this solution, so this reaction is exothermic. It's giving off heat to the solution that is surrounding the reaction. And we are going to, of course, plus heat be given off. In other words, we can calculate the delta H of this reaction with this information, and that is what we're wanting to do. Now we know that the heat of the reaction is equal to the negative heat of the surroundings. The surroundings is the solution that's being formed. Now this reaction is taking place, but the pieces, the substance themselves, are warming up, and the water that it was dissolving in is warming up by this 3.43 degrees. So I want you to think about what is the mass of the surroundings before we go any further. So stop and choose your answer and then resume. Okay. This is a little bit nuanced here, but I hope you put C, that the solution would be 306 grams. Now, I say it's a little nuanced here. Let's make sure we understand why this would be. When this reaction takes place, bonds are broken. It's releasing heat. So heat is coming out of this reaction. Where is that heat going? Well, that heat is going into that coffee cup calorimeter, and all of that water and the calcium and chloride ions are both heating up. Whoops, yep, there's two of these. That's a little messy, but it doesn't matter. We've got the calcium, we've got the chloride in there. Everything that's in there is actually warming up. So energy is coming out of breaking that connection between those guys. Energy is being released. It is going into everything. Well, we have 300 milliliters of water. Water has a density equal to 1 gram per milliliter. I want you to know that. And I want you to realize that if you know the volume of water in milliliters, you know the grams of water you know the mass of water in grams. So I have those 300 grams there, plus I have the 6 grams due to the calcium chloride, and that is where that's coming from. So let's move to the light board now, and let's work this problem. It's calorimetry. It is a challenge for us. But let's see how it works here. We know that the heat of the reaction is what I want to know. I can monitor what's happening with the solution there. So let's see what the solution is made of. So the Q of the reaction is the mass of the solution, the specific heat capacity of the solution, and the change in temperature of the solution. Well, I know all of those pieces. The mass of the solution we just spent some time talking about is 306 grams. The specific heat of the solution is 4.18. It's just that of water because it's mostly water, and they gave that to me. You don't have to memorize that value. The change in temperature, they didn't give me a final and initial, but they said that it rose by 3.43 degrees Celsius. So this gives us the heat of the reaction. Let's multiply those values out, and I got, in joules, a negative 4.39 times 10 to the third joules. Okay, and that would be, in kilojoules, a negative 4.39 kilojoules. So when you make a solution, we don't typically get a lot of energy out. And let's remember that this is not now going to be the delta H of that reaction, because when we look at that reaction, how much calcium chloride is being depicted there? It's a whole mole, okay? So we might need to know the delta H for a whole mole of calcium chloride. And how much calcium chloride do we actually have? We have 6 grams. So what I know at this point is that there is this many kilojoules of heat for every 6 grams of calcium chloride. And there is my dimensional analysis unit factor that I can use. I know this relationship, but I don't want to know it for 6 grams. So I'm going to look at my balanced equation and see that I have 1 mole of calcium chloride. I want to know the kilojoules for 1 mole. Now, I can't use this relationship until I turn this into grams. So I'll say I don't want moles of calcium chloride. I want grams of calcium chloride. I go to the periodic table and I come up with the molar mass of calcium chloride, which is 110.98 grams in a mole. Now, I've gotten rid of my moles. Why did I want to do that? I want to be able to use this relationship. So I can now go from grams of calcium chloride to kilojoules, because that's what I want to know, the kilojoules that 1 mole would be producing. And I'll put my numbers with that. I have a negative 4.39 here. I have a 6 there. And this will give me the energy released when 1 mole of calcium chloride dissolves. This is a value of a negative 81.2, and the unit would be kilojoules. So now I can put in what the delta H of this reaction is. It is this value. Now I will want to tell you that what I've done here is a typical way of getting to that value, but it's not the only way that you can get to that value. You could say I need to know it for kilojoules per mole of calcium chloride, because that's what the balanced equation is. It's kilojoules per 1 mole of calcium chloride. And you could just do dimensional analysis with this and convert your grams to moles. There's a lot of different ways you can get there, but what you need to make sure you understand is when you're determining a delta H for a reaction, you need it for as it's balanced. You have to know it for as it's balanced. And it's balanced for 1 mole, so you need to know the energy for 1 mole, not the energy for 6 grams. Typically, students don't struggle with this part. They can do this. What they struggle with is relating that to the balanced equation and doing that last step, getting the quantity that we know it for from the what was put into the chamber versus the quantity that the balanced equation has. And we'll practice doing this in class, I promise. We'll work on this a lot, trying to make sure we get the nuanced understanding of how to go from the Q of the reaction for the quantity in the chamber, in the calorimetry chamber, versus getting the energy for the balanced equation. All right, let's look at another problem here. Okay, so we have another problem here. It is not a standard calorimetry problem, but it uses all the concepts of calorimetry within it. And I've got it here because I really want to drive home the difference between the delta H of the reaction versus the delta H for the given quantity. So if we look at this problem, and I'll write on the screen a little bit as we kind of highlight information that's given to us, we see that this reaction is taking place, and we want to know how much of this, okay, how many moles of this is going to be needed in order to take 100 milliliters of water, which we know is also 200 milliliters, which is 200 grams of water, and heat it up from 20 degrees Celsius right up to the boiling point, 100 degrees Celsius. And then it has a little twist, and that is when this reaction takes place, only half of it, 50%, actually is heating up the water. The other half is just going out into the surroundings. So 50% is heating up the water, and the rest of it is being lost beyond the water. Okay, so let us get to the light board here, and let's start working through this problem. We know that whatever the reaction is doing, the surroundings is doing the same thing but opposite in sign. But in this case, the surroundings made up of two things. It is the water heating up plus everything else. Okay? And I'll just write everything else that surrounds it. Okay, so that is what I know that the surroundings is. Now let's think about this. 50% of it's going to the water. So half of the heat of the surrounding is here, and the other half is right there. So let's just ponder that. How are we going to get that down to what I know? I know that whatever the reaction is doing, half of it is going into the water. That would be one way to do it. And the other half is going into everything else. What I want to know is, as I heat up the water, what's the heat of the reaction, and actually take it one step further, figure out the amount of methane, CH4, it's going to take to heat that up. So what do I could write it this way, that the Q of the reaction is equal to 2 times the Q of the water. Because if I took the heat of the water, half of it went in from this reaction, went into that, and I doubled it, that would be all the heat of the reaction. So a lot of different ways of thinking about this, and it might be helpful for you to stop, back up, and say, what did she just say? How do I get this relationship? But once we have an understanding of this relationship, now we can take that water and we can break it out. We have the mass of the water. We have the specific, C, that's a C. C sub S of the water, okay? And we have the change in temperature of the water. All of those are about the water. We can plug those numbers in. So what's the mass of the water? It was 200 grams. The specific heat capacity of the water, 4.1, do they give it to you in here? No, okay. 4.184 is the value, you can know it to actually 4 significant figures if you looked it up, joules per gram degrees Celsius, and you don't have to memorize that. You will be provided with it on tests. You can look it up when you're doing your homework. The change in temperature is going from 100 degrees Celsius, actually it's going up to 100 degrees Celsius from 20. And is it 20.0? No, it's just listed as 20 degrees Celsius. Okay? So when I multiply that out, that's going to give me the amount of heat this reaction needs to be generating in order to heat my water up by this amount. And this gives me a value of 1.34, and it's actually negative 1.34 times 10 to the 5th joules. Okay, if I wanted to know that in kilojoules, that would be a negative 134 kilojoules. So you can convert by moving the decimal place over 3 to kilojoules. So that's how much heat I need. I need this much heat from the reaction to heat up my water from 20 up to 100 degrees. But what they want to know is, how many moles of methane is that going to require? So I'm going to take my negative 134 kilojoules and say, I don't want to know the amount of energy it took to heat it up. That's this number. What I want to know is how many moles of methane will that require. Then I go to my balanced thermochemical equation that's given to me there on the screen. It's a negative 890.4. Oops, it doesn't go there. My bad. Negative 890.4. It goes with the kilojoules. What goes with the moles? Well, if I look at the balanced equation, I see that I have 1 mole of the CH4. So when I divide this out, it's going to tell me how many moles of methane I need, and it's 0.150 moles of methane. So again, we're making opposite relationship here. We know the delta H for the thermochemical equation, and we're trying to get the amount of substance. In the previous problem, we got the energy for an amount, and we wanted to relate that back to a balanced thermochemical equation. Those are the two things that we do with calorimetry more typically when we're making these measurements of how temperature changes to the surroundings. Okay, so this ends our discussion of calorimetry for now. We will practice it a lot in class and really try to work on understanding these connections between the energy of the reaction and the energy for the amount that's actually in the calorimetry chamber, making measurements of temperature changes to make those relationships happen.